This video goes with Unit 13, which is nuclear chemistry. The essential questions are: what is the difference between nuclear fission and nuclear fusion? Where do we use these reactions? And what is mass energy equivalence? So we're going to look first at nuclear power plants. Okay, we have these all over the country. They help provide power for our lifestyles. And so here's a kind of a schematic of a power plant. And in the core, which is that first area, that's where the nuclear reactions happen. And this in particular is nuclear fission. Fission is where the nucleus is split apart and it releases a whole lot of energy, which we're able to then harness and use for electricity. This is an example of artificial fission, which means it's man-made. It's not happening naturally. Okay, so fission, just to give you an example here, this is uranium-235, and we have a stray neutron going into that. Well, that makes it unstable, and it's uranium-236 now because it has an extra neutron. So it fissions, which means it breaks apart, and that releases a few more neutrons and makes two new elements. Okay, so this is natural fission, and it can be done artificially, but can be used in West Africa to produce power. Fusion, on the other hand, is the opposite. They're being fused together, nuclei, small nuclei are coming together, and it also releases energy, and this is what fuels the sun and stars. Okay, so in the sun, or in a star, you have different types of hydrogen, different isotopes. We've got hydrogen, deuterium, tritium, and that comes together to make helium and an extra neutron. This is an example of natural fusion. It's happening naturally. Okay, on the other side, artificial fusion, an example of that would be the hydrogen bomb. And we would like to use fusion to produce power, but we have not yet found a way to harness it. And they touched on this in Spider-Man 2. He was trying to use fusion to harness energy. Okay, so now let's look at another example of fusion. So we take a hydrogen, which has a mass of 1.6727 times 10 to the negative 27 kilograms, very, very small. And we take deuterium, which is hydrogen with a neutron, and it has double the mass because the neutron and proton weigh the same. So that's going to give me a total mass of 5.0164 times 10 to the negative 27th. But if I look at my helium over here, I don't have quite that much. I'm missing just a little bit. Okay, so where did that extra mass go? Well, what happens is the mass was converted into energy, and this comes from Einstein's E equals mc squared. So the difference is right there. It's a very small amount. So we're going to multiply it by the speed of light squared, and that's how much energy was released by that one little reaction. It's not very much, but when that happens over and over again, that adds up to a lot, like what's happening in the sun. This is the measured energy release, and this is what we call mass energy equivalent. So when it loses mass, it kind of releases it as energy. So to go to some uses for the radioactive isotopes, which are radioisotopes, these are the ones that like to decay. We can use medical imaging and cancer treatment. Okay, and so those are different radioactive isotopes that they can use in these treatments. Iodine-131 is used for diagnosing different things. Besides in medicine, we can also use it for nuclear energy and weapons and power plants. Uranium-235 we have used in the atomic bomb. We can use it in carbon dating, which allows us to tell how old fossils are. And that's using carbon-14. Okay, so we're going to compare real quick the nuclear reactions to chemical reactions. So a chemical reaction would be like burning coal. Nuclear reaction would be like fission or fusion. So the particles involved in a chemical reaction are we're exchanging electrons. In a nuclear reaction, you're exchanging protons or neutrons. In the identity of the element, it's unchanged. It just rearranges the atoms and it might bind them together to make a compound. In a nuclear reaction, it actually changes one element into another. The energy change of a chemical reaction is very small, and the energy in a nuclear reaction is huge, and we can use that E equals mc squared to help us figure that out.